Our task was to derive an equation that could be used to find the heights needed for two toilet paper rolls to hit the ground at the same time. One of these rolls would be held so it would unravel, and one of these rolls would be normally dropped. In order to complete this task, a knowledge of kinematics and a knowledge of rotational motion is required.
Toilet paper challenge using toric and parallel axis theorem. Step 1. Kinematic calculations. Using one of the kinematic formulas, d is equal to vi delta t plus 1/2 a delta t squared. For the straight drop, t is equal to the square root of 2 big H divided by gravity. For the unrolling drop, t is equal to the square root of 2h divided by acceleration. Time of the dropping toilet paper roll is equal to the time of the unrolling toilet paper roll. So big H over little h is equal to gravity over acceleration. Determining the acceleration using toric and parallel axis theorem. Using the parallel axis theorem, which is I is equal to 1/2 m bracket r squared little plus big R squared close bracket plus m big R squared is equal to 1/2 m open bracket r squared plus 3 big R squared close bracket. You plug that into the toric formula, which is equal to toric is equal to inertia times angular acceleration. Angular acceleration is equal to toric over inertia. Toric in this case is mgr due to the pivot point being pivot point A, which inevitably gets to the 2gr big R over small r squared plus 3 big R squared. You plug in the angular acceleration into the acceleration formula. So tangential acceleration is equal to angular acceleration times radius, and you get 2 times gravity big R squared divided by small r squared plus 3 big R squared. Finally, you plug in the acceleration into the kinematic formula that we got from step 1, and you get 3 over 2 plus r squared over 2 big R squared is equal to big H over little h. Solving for little h, which is the height of the unrolling toilet paper roll, we get small h is equal to big H divided by 3 over 2 plus r squared over 2 big R squared. That is the derivation of the formula for the height of the unrolling toilet paper roll.
We assumed the toilet paper rolls would all have the same size and weight. We also assumed that they would all be perfectly circular. Although this was not the case, we did our best to ensure that the toilet paper that was used for unraveling was indeed circular. We also assumed that the radius of the toilet paper that was being unrolled would not change when traveling through the air. One major source of error in our experiment was that when we dropped the normal toilet paper roll, the one that was not unraveling, it did have some rotation to it, which could have affected the results slightly.